Thank you. Go ahead, please.
Okay, great. Well, let me just share screen and get started. Good morning, good afternoon, good evening, everyone. We are now at the start of week 2 of this rather intense and exciting school. So today I want to tell you a little bit about pre-geometry, formal language, and how this relates to the Wolfram Physics project, and maybe some applications to quantum gravity. Okay, let me just clear a few things here. So all right. All right. So in today's talk, these three topics are quite central to what we are going to discuss. In a way, I should, before I start the actual content of the talk, I should tell you a little bit about why I'm talking about these things, and also how you can relate these things to other things that you heard through the school from various speakers. Now, just to, I mean, this talk will largely be based on a couple of publications, which you can see on this list here. I would like to acknowledge my collaborators, Hatem, and who you know very well, and Dean Rickles, who's a professor at University of Sydney, with whom quite a bit of the work I'm going to talk about today has been worked on, and you can find these publications. I think all of these works are there in your recommended reading, or if not, you can ask me later. And perhaps I'll touch upon a few other things which I've not included in this list. They may be related topics. So, as I said, before I actually start talking about pre-geometry per se, I want to tell you a little bit about what this talk is about, in the sense at a kind of more general level. So my own interest in the physics project right from the beginning has been in the foundations. Like we've seen all these interesting and quite kind of amazing computational models from which we've done all sorts of explorations. We look at models of all kinds of structure, from complex systems to fundamental physics. And the kind of question for me is that what is the formal foundation of these kind of explorations when you use these rewrite rules, when you try to build systems this way from bottom up? What is the formal foundations? And when I say formal foundations, I am most of the time interested in mathematical foundations. So my interest in physics foundations, there are many ways in which people can pursue an interest in the foundations of physics, and there are many approaches. My approach is to seek mathematical structures that give some validity to certain formal theories. So if you have theories of gravity or of quantum field theories or etc., I am more interested in the mathematical structures than in trying to compute maybe some particle interactions. Both of these things are interesting, but I'm just telling you what I'm interested in and why. Therefore, this talk will be addressing certain mathematical structures behind these things. So that is one thing. And to me, it's never enough to have a computational model. There has to be some formal foundations. We just have to find it. And that's much of the kind of pursuit that I follow. Now, I hope that through this talk, I can kind of give you some sense of what mathematical formalism could be behind all these computational models that you see in the physics project. And I also kind of want to put in context how all these things can be seen together. So, I mean, typically, if you look at the way theoretical physics is typically done, in theoretical physics or even in mathematical physics, there are certain phenomena or properties, physical or mathematical, and we try to have two kinds of explanations. One would be a kind of mathematical explanation, and one would be a computational explanation. In the mathematical explanation, we try to come up with so-called phenomenological theories, meaning that I'm using the word phenomenological broadly, meaning we come up with a theory that either gives us the equations of motion or the dynamics of that particular phenomena. So if that phenomena is maybe the motion of stars or the motion of the subatomic particles, whatever, we come up with some equation of motion or some such description that describes the kinetics or the kinematics or the dynamics of that system. So that is a kind of mathematical theory, a mathematical explanation for that phenomena. Then on the computational side, we have simulations, meaning we take those theoretical differential equations or whatever they may be, and we simulate that system with those equations of motion. We try to simulate the solutions, and or we use those simulations to study how the system may evolve and so on. So that's the kind of very standard way in which theoretical physics explorations are done, theory and simulations. I'm not talking about experiment at this point. I'm just talking about the theory side. Okay. Now, there is more to this. This is not all, even in standard theoretical physics. So first, let me just say about computational explorations. In computational models, besides simulations, you can do something more. You can even do things what are sometimes called emulations. Now, in the physics terminology, people use it. They may not call it that way all the time, but for example, engineers in engineering, like theoretical engineering, a lot of things are emulating. What is emulating? Emulating means you try to mimic a system using something else. Emulation doesn't always have to be a experimental physical emulation. It can also be a theoretical emulation. So typical examples of emulations are where you may not have access to a differential equation or an equation of motion, but you may say that here are certain objects and they have these properties. Give them the rules, give them or endow these objects with certain laws of motion or certain properties. Let them interact and let them do their thing. Like you take a bunch of particles which are representing gas molecules, you give them some rules of how they can attract, repel, and you let them do their thing. Similar to cellular automata, rewriting systems, so on. So those are computational models which are emulating the system. You don't have a priori necessarily a kind of fluid equation or a ODE or a PDE, but you have some underlying local rules and you let the system do its thing because you don't know what the actual equation of motion is. But when you let the system do its thing, you're literally kind of emulating the dynamics or the kinematics of that. So much of what you've seen in the physics project, especially with these rewrite rules, are emulations of such things. Now, typically, one would be convinced of an emulation if it comes from some theoretical setting, because an emulation doesn't directly come from a differential equation. It comes from a different kind of theoretical setting. So if you just see an emulation of some system, you may say, yeah, this is nice, but what's the thing behind it? So that's the kind of question I want to answer here with the theoretical or mathematical foundations. The mathematical foundations of any theory of physics or mathematics for that matter is an abstract formalism that gives an explanation of where these equations of motion or where these dynamics come from, what are the underlying structures, where do the structures come from. So if you take a typical theory of physics, you have certain physical structures that are assumed and some properties. It is perfectly a valid question to ask, where do these physical structures come from? Why are we assuming this? I mean, it's not that you always have to ask that thing. It depends what you're trying to, what's the level at which you're exploring something. So you may ask, where do they come from? Like there's some certain assumptions that there is space-time and space-time may have certain properties, quantum or classical. You can ask, where does this thing that we call space-time come from? What endows its certain properties and structures? Those are questions that are asked at the foundations. And here, what I'm attempting to do is to probe that level of explanation. If we are able to say something about a mathematical formalism of the foundations at that level, then it becomes clear where the more practical kind of phenomenology comes from, and it also becomes clear what this emulation represents. So all the computer models that you see with rewrite systems, I want to tell you that they represent something fundamental. They represent something underlying the formalism of what could be theoretical physics. I'm not saying we've cracked the whole formalism. I'm saying this is the way one can try to start making sense of the structures behind any kind of physical theory more formally. When I say formally, I mean mathematically. So that is what this kind of exploration is about. In a way, like is always in the case of any kind of approach to the foundations of physics, you may say that, well, I mean, when you're trying to ask what the basic structures are, you're really not talking about a theory, but one is talking about a meta theory. One is asking what is the structure of structures, meaning what is the what is the abstract structure of the physical structures with which we describe physics. And that's precisely what foundations are often about. They are about structureless structure, or the structure of structures, however you want to think about it. And in some sense, this almost seems like it is not exactly about physics, but it's more about metaphysics. And to a large extent, that is correct. These kind of explorations of metastructures or meta theories of structures, largely you could call these metaphysical approaches. And I'm interested in a mathematical formalism of such a metaphysics. Also, I want to, as you go through this talk, I'll want to impress this point that when we say metaphysics, of course, metaphysics is itself very broad. Philosophers describe it way more broadly. I'm referring to this more in the context of the theory of philosophy and theories of physics. So I'm talking the metaphysics of physics, as in pre-physics, or what might be the building blocks of physics. This is what the way I'll present this. What we call, or what we try to see as metaphysics over here, will be very closely related to what is otherwise called as meta-mathematics in the foundations of mathematics. And similar questions that mathematicians are currently asking, I mean, as we speak, on various in various groups around the world, mathematicians are also asking what is the right way, formalism to build the foundations of mathematics. This has been a kind of age-old question. And I mean, in the textbook approach, first people thought 100 years ago, maybe set theory is the right place to build off all of mathematics. Then they said, oh no, set theory has problems. Maybe we need category theory, we need other things, and so on. The kind of, I would not say conclusions, but the kind of realizations that have come up now in the foundations of mathematics and metamath are, I would say, to the way I'm presenting this, are the same kind of issues that are there at the foundations of physics. And in a way, as a physicist, I feel that learning about the foundations of mathematics is directly informing us about the foundations of physics. And that's what I want to, that's the kind of point I want to drive today. And as you see, when I say mathematics, I'm not only talking about mathematics. There is a very close nexus between physics, mathematics, and computer science, or computation in the fundamental sense. And towards, as we proceed, I'll try to make this link between proofs, formal programs, and physics. These three things at an abstract level or at a meta-theoretic level are quite similar structures, or they are quite equivalent in some sense. So that's the kind of setup I want to drive towards, and that's where all this stands. Okay, and so let's proceed along these lines. Now, to keep things in focus, I'm not trying to talk about a theory of everything or about a theory of all of foundations. So I will start with a narrower scope, and then we can broaden out as things go. I'll try to first talk about pregeometry, and then I'll try to, first I have to tell you what I mean by pregeometry, and then I'll touch upon a little bit of earlier work done by various very deep thinkers in very deep thinking physicists who have also done some things. But somehow foundations is a kind of topic that often has been simmering for years. But there are lots of distractions in the real world with practical problems. So sometimes foundations don't get the attention they should. So that's where I want to put some more attention here. And once I talk a little bit about pregeometry, I want to tell you why I think formal languages actually give us the tools to address these questions and to build such a formalism. And what I mean by formal language, I will define all those things. By the time towards the end, I actually come to I try to answer this question that where does space come from? We always talk about various spaces in physics. We say, let's assume that there's this type of space or that type of space. It can be physical space or mathematical space, Hilbert spaces or ordinary Minkowski space, Lorentzian spaces, whatever. I want to start asking the question that mathematically, what are spaces, or where do they really come from? Is there a way we can abstractly understand how spaces themselves come out? Now, in a way, this is similar to things like, like physicists say, where the emergence of space-time and all, but I'm not really talking about at a very phenomenological level. I'm asking where, even for a mathematician, where do spaces come from? And some of the answers that mathematicians themselves have come up in this with respect to such a question are what I think are very relevant to physics. Okay, so now by pregeometry, the term pregeometry was first coined by John Wheeler. Those of you who are physicists here will, of course, know John Wheeler from various things. Very, very well-known physicist. He's also author of this big fat book on general relativity, Miss Nathan Wheeler. But Wheeler, like in those days, physicists were natural philosophers. They were not only thinking about solving or computing or solving practical problems in physics, but they were also very deeply thinking about the foundations, not just of gravity or of quantum, but also about how these might reconcile and things like that. So for Wheeler, he had this thinking that, look, physical, this is almost a metaphysical philosophical thinking he had. He used to think that physical substrates cannot be the most fundamental, because if it were, then you'll keep asking, where does it come from, and you'll keep doing this infinitely many, like an infinite tower, and it'll never end. So there seems to be something missing in such a level of explanation. And then he also said that, look, the universe can collapse, and when the universe collapses, it takes away space, time, matter, and even law with it. So there has to be something that transcends physical structure as we know it. And for Wheeler, he had this kind of conception that there must be something other than physical structure in terms of space, time, and matter, and that should be thought of as the fundamental building blocks of the universe. In fact, that should be the thing that builds the universe, and that's how the universe comes into being. So for him, he often asks the question, it's not like we should think about physics in a way that we think about physics classically, then we quantize it, we apply some procedure, and then think about it more fundamentally. That seems very artificial. For Wheeler, it was, what are the methods and materials by which nature constructs herself, and how the universe comes into being from a more physical substrate. So he kept asking this question. Of course, they were not. It's not like everything has an answer, but sometimes a good question leads to many things. And that kind of thinking led Wheeler to this famous "it from bit" quote. And as many of you who are physicists know, this "it from bit" basically takes the stance that information is fundamental. Now, of course, various physicists will say various things on what is fundamental. Wheeler had many ideas. He did think that there is something more abstract, and he had various proposals for this thing, not only information. Information was just one of them. At some point, he also thought that we should think of something like abstract propositional calculus, some sort of abstract logic, so almost like an abstract mathematical structure that should be the building blocks, and from that everything reality emerges. At other points he said that perhaps we should not ignore the role of the observer. There were many interesting things, but I'm just going to focus on the pregeometry part of it. So this kind of way of thinking about basic building blocks is a very fundamentally constructivist approach. Constructivist means nothing exists a priori. It has to be built from scratch. And then you have to think about what the building blocks are. They can't be physical, because physical things also have to be built from scratch. And so the question is, what exactly should be the mathematical formalism from which any of these things can actually be constructed? So let me move this a little away. 1 minute, please. Okay. Yeah, the Zoom bar was coming a little bit my way. Okay. So in some sense, for Wheeler, even the laws of physics as we know it were not necessarily the fundamental thing. He wanted to even ask questions like, where do the laws come from? And now, at that time, Wheeler did not have all the mathematical tools that we have today. So, along the years, besides Wheeler, a few other people also started thinking about this and similar questions. So one of them was Chris Isham, who's still alive, and Andreas Doring, who's also alive, I think. Chris Isham is now a very senior emeritus professor at Imperial College, and Andreas was a student or postdoc of his at that time. And about in 2008, now that's a while back, they started thinking about the so-called topos theoretic foundations for physics. In a way, they were not exactly answering the questions at the same level as Wheeler, but they were also looking for something in a similar spirit. I'll tell you, I'll describe, you'll hear a couple of terms like topos and this and that, formal language. I will define all these things as we go by. So if there is anything that I say I've not at some point soon enough, if I've not told you or defined it, please stop me, just ask what it is, and that's perfectly fine. So feel free to interrupt me at any point for that matter. Okay, so what Aishem and Doring were doing is they were also looking for an abstract structural foundations. And for them, the motivation was a little bit more simple-minded compared to Wheeler's very grand scheme of building blocks. What they were asking is that, well, we need some abstract structural framework from which new physical theories can be formally constructed, including the ones that we observe and others. So for them, one of the motivations was that, by the way, you can see my cursor, right? Yeah. Okay. So one of the motivations for Aishem and Doring was that we should allow for, in this more general framework, we should allow for the fact that physical observables need not assume continuous values. And in many ways, they were also, like Wheeler, they were also motivated by these questions of quantum gravity. Now, for Wheeler, he wanted to see something even more abstract. For these guys, what they were saying is that, well, if quantum gravity is truly has the properties of quantum and gravity in one, at least we should allow for some framework within which various theories can be formulated. So in a sense, they were also thinking of some sort of meta theory within which various physical theories like classical mechanics, quantum mechanics, and also maybe some approaches to quantum gravity could be formalized, where the setup was so general that you need not assume physical observables to be continuous. And for them, they struck upon this particular so-called topos theoretic framework, which essentially is trying to say that for every physical theory, you can formalize it in terms of a formal language. So a formal language gives you a representation of physical theories. Now, what is a formal language and why is that interesting? Now, before I tell you that, let me just say a little bit about what toposes themselves are, so that if you know what toposes are, then you can then it'll give you a good idea about. Wait, you still see the whole screen, right? Okay, great. Because sometimes if I switch to the screen, I can't see the zoom and vice versa. So if I ask, feel free to just say. Okay, so let's talk a little bit about what toposes are. Now, many of the things I'm saying are things that you may come across if you're looking at maybe abstract foundations of mathematics. Some of this is part of what is called category theory. And some of these things are things that people who work in formal computer science, formal programs and formal proof theory, that's where some of these ideas are being borrowed from. And they turn out to be useful for such kind of discussions on the foundations. So in mathematics, a category is just a category is basically, there are many ways to describe it. You can write it down formally, etc. But at this level of a kind of slightly general crowd, the way I like to introduce what a category is, it's really a abstract formalism of relations. In a category, you don't care about what the meaning of objects are. You have some objects, they can be of some kind, doesn't matter what they are, and there are some relations between objects. And much of what you do in category theory is about relationality. And in many ways, category theory can be seen as a formal mathematical approach to deal with relations. And toposes are a particular kind of category that has certain set theory-like properties. Now, why set theory? Because in much of standard classical mathematics, set theory is the kind, at least from the textbook perspective, as things are introduced, set theory is often the basics or the foundations. Everything is built upon upon set theoretic ideas. You can even do logical operations with intersection and unions of sets and all that kind of things. So what mathematicians realize is we need something that is a little bit more fundamental and abstract than set theory, because set theory does have some problems. And now I'm not going to discuss those, but those of you who know it, for example, the history of logic, you will see that there were certain logical paradoxes, Russell's paradox and other things, for which people realize that set theory may not be enough. And a lot of modern foundations of mathematics are done using category theory, which kind of generalizes things a little bit more, focuses on relations a little bit more, but it also comes at the cost of making things more abstract. But anyway, that abstraction can be useful for certain contexts. It's not like, like, as you know, just because something is more fundamental, that doesn't mean it's going to explain everything. In the same way, like, just because physics may be so to say, quote unquote, the building block of chemistry, it doesn't mean physics will explain chemistry or chemistry will explain all of biology. We already know that. Even though at the fundamental level, there may be certain rules that tell you how structures come, like how physics may give you some intuition about how structures for chemistry or biology come. Physics by itself, or the theories of physics by itself, isn't going to give you a complete explanation of chemistry and biology, because at every level, the nature of uh, structures and beings is such that there are laws and theories almost at every level. You cannot just explain everything in a reductionist way. In that same way, even when we explain the foundations of physics, it's not that just because you're talking about some physical building blocks or foundations, you're going to derive all of classical and standard physics just that way. You're going to address things. You're going to rather answer questions like, where do these structures come from? Why does you may ask, like, why does a classical theory or a quantum theory have this particular spatial structure or that particular property? What is the general formalism within which it is defined? Why some other theories may not be defined and why certain other theories may be defined? You can ask those type of questions. It's not like the game of foundations is not about deriving everything, because the world is not the world and physics and nature and mathematics are not necessarily always reducible. So I mean, keep that in mind. So okay, so just as set theory gave us a lot of good properties to work with in terms of some kind of formalism at the basics of math, similarly, certain types of categories which have set theory like properties but not the problems of set theory, they are called toposes. Toposes are these class of a formal theory of relations that gives you some room for interesting mathematical manipulations like you could do with set theory. So with set theory, for example, you may do some logical operations. Similarly, with toposes, you can do some nice logical operations. With toposes, you can define certain things like a subset, or some things like a singleton set or an empty set, or the analog of that, if not exactly that thing. So in these toposes, you can define those things abstractly and do certain operations. Now, one interesting theorem that happens to be with topos theory is that within a topos, you can define some notion of what is a subobject, which is a mathematical analog of a subset in set theory. And this has the interesting property that, unlike set theory, where the subsets of set theory satisfy realize a Boolean algebra, the subobjects or the analog of subsets of topos theory analyze a Heyting algebra. A Heyting algebra is slightly more general than a Boolean algebra, and this generalization is quite key to what will follow. And I'll say what it is. In one of the key points is that Heyting algebra takes you from classical logic to intuitionistic logic. And intuitionistic logic is the logic behind computer science. Computer science isn't based on good old classical logic, and I'll tell you why. It's based on intuitionistic logic. And toposes with their natural connection to this Heyting algebra, which generalizes Boolean algebra and therefore generalizes standard logic that you may be using in the classical setup, give you a very nice implicit connection to formal computation, and that will become very useful. So keep in mind that I'm trying to, at this point, I'm building up the story so that we start seeing the relation between formal proofs in mathematics, formal programs in computer science, and physics. So toposes, in some sense, topos is actually a Greek word for place, and toposes are places where mathematics can be built. That's literally what it is. Okay, so as I said, that now in topos theories, what we'll do is so a topos theory is a place where mathematics can be built. But what you may ask, okay, fine, it's a place, but within that place, what are the structures that can exist or what can be built? So what happens is that within a topos, in the kind of general abstract setting that toposes are defined, every topos is always endowed with some formal language sitting within it. Now, at this point, I've not told you what is a formal language. So think about it this way, that every topos has some building blocks which you can see as formal proofs. So what I'll be driving towards is will be certain things called type theories. At this point, I've not spoken on type theories, so just keep the word in mind. But type theories are the building blocks of formal languages, and within every topos, you can express various languages. So think about it this way: a topos is a place. Within this place, you have you have certain kind of constructions that can exist, mathematical or abstract constructions, and these constructions can realize various formal systems or formal languages. In this case, you can think about it this way, that based on that based on the properties of that place, because not every a topos is not one thing. There are many types of toposes, and depending on the type of topos, that particular topos will have some formal operations that are allowed within that space. And based on that formal operations, you can build a whole formal system. You can think of this as at this point, you can think of it as a formal mathematical system. And this formal mathematical system is basically a formal language. Again, you'll see what a formal language is. So these toposes basically have they have inbuilt within them this very constructivist approach. By constructivist, it means in the mathematical sense, constructivist means that you don't assume anything. You just have some very basic building blocks, and from that you can compose and build stuff. So this is the reason why compositionality and composition is crucial and almost a fundamental feature of all of these kind of things that we are going to talk about. In fact, compositionality is at the heart of every theoretical construction at this level of topos theory or building blocks of physics, or even rewriting systems. Everything is about what are the rules of composing. If you have objects and there are relations between the objects, what are the ways in which you can compose these objects? You can compose relations between the objects. You can compose relations between relations, and so on. So compositionality and the way you can bring things together to get a new thing is at the heart of everything that we discuss. And in formal theories of mathematics, there are all ways in which you can define compositionality. So, for example, if you take a particular given algebra, an abstract algebra or whatever, over there, the simplest example of a composition is just your product, the binary product or any other product for that matter. When you write down the definition of a product, that's your simplest composition. That composition gives that algebra some interesting properties, and it literally gives you a way to build all the elements or the words of that algebra from that composition based on the fundamental thing. So this is what constructivist mathematics is about. And also constructivist physics will turn out to be that way. But right now, I'm not even talking about physics. I'm just talking about I'm just talking about things more at a meta-mathematical level, and then we'll try to see how these meta-mathematical objects motivate what may be the metaphysical building blocks of physics. Okay, so one of the things in these topos theoretic approaches is that based on this intuitionistic logic, which is very innate to a topos theoretic framework, one of the important things about intuitionistic logic is that apart from the usual kind of rules that you have in standard logic, one of the important things is that the law of the excluded middle does not necessarily hold. Now, what is the law of the excluded middle? In standard logic, in classical logic or so, you may be aware of this textbook statement that if you have a proposition and you have its negation, so if you have a proposition not and, this or this will be one. That means either this is true or this is true. You take a proposition, either it's true or false, and depending on whether it's true or false, its negation will have the opposite truth value. So it can either be a given proposition can either be true or false. They cannot be anything other than that. But in computer science, we know from a lot of problems like the halting problem, Entscheidungs problem, undecidability, it is not always the case that a proposition can be true or false. There are propositions, or rather problems, if you want to say, like theoretical problems, which are neither true nor false. They are simply undecidable. And computer science is full of undecidability because formal computation is all about constructivist, is all about a constructivist formalism. Formal computation is basically based on this intuitionistic logic, which allows for undecidability. And as you see, when you write a formal program, you cannot write a program in which you're trying to solve a problem, and you cannot say that, well, the solution to the problem is, since this case doesn't exist, therefore the opposite or the negation must be true. You cannot prove a program like that. You have to actually compute something. Otherwise, it is because in formal computation, that, like, okay, you may think of more general forms of computation with different types of logic and so on. But right now, I'm just talking about standard computation built on lambda calculus and so on. They are all based on intuitionistic logic and formal proof systems, or I mean, in a sense, a formal program is just a formal proof system. There are some initial states, which are the axioms. Then you have some laws of inference, and then you arrive at a result, which starting from this, you say that this proves that the initial state is somehow equivalent to the final state. You compute the thing, and through computation. So computation formally is nothing but a proof system. And that is based on certain types of logic and certain types of inference rules. And in computer science, it is necessarily based on this kind of framework of intuitionistic logic. And that is why you get problems which are undecidable. And that's just a fact of life. I mean, you can think of other things like hypercomputation and so on. So essentially, in constructivist mathematics, if you work with that setup, then you have to admit this property, that a proposition can be undecidable, meaning that, in other words, there are certain things that you can evaluate or you can compute and determine its truth value, and other things you cannot. They are uncomputable or computationally irreducible. Different ways that you can describe it. That's really a inherent feature of computation. And these kind of features of computation, they are not bugs. They are really features, in the same way like a lot of the things that are there in Gödel's incompleteness theorem. Those are features of formal systems. And and it's not part of this talk, but you may separately even try to explore in what sense certain properties of these incompleteness theorems have something to strongly do with formal computation. So in formal computation, when you solve a problem, you cannot solve by you cannot allow for a proof by contradiction. A proof by contradiction means assume the opposite holds. You prove that that's not the case, and therefore the statement is true. Proof by contradictions are not allowed in a formal in a formal program. You have to actually compute the thing, otherwise the program will never end. And the same way in constructivist mathematics, based on intuitionistic logic, proofs by contradiction are not allowed, because precisely this thing holds that just proving true or false is not enough. Something can be undecidable. And that is what is at the heart of constructivist mathematics. And mathematicians who are trying to work on those mathematical foundations are trying to take these ideas of computation very seriously as the building blocks of mathematics itself. And here we are trying to say that that's actually very relevant for physics itself. Now, you may say that, well, I mean, in computer science, it's the programmer who does the computation. So if you're talking about physics or math, who's doing the programming? Who's the programmer? Here we are trying to say that nature is itself the programmer. Nature's own kind of things. Nature itself is a giant system of computation. And this means that many things can be computed and other things are computationally irreducible or non-computable. We are trying to say that the building blocks, the way they can compose, the way they can form structures, the way these structures realize relations and connections, or the way they realize equivalences between other structures, all this at an abstract level is a computational process. And this computational process can be formalized now in terms of some of these formal frameworks. So again, much of what I'm saying, I'm not trying to actually tell you much about the theory of reality as such, nor am I trying to answer an ontological question of philosophy. The goal of what we are doing here is to try to formalize or when I say formalize, I mean to provide a mathematical description of how such a system can be, with the goal that if such a formal system can describe physical structures, then this is the mathematical framework that will give you a representation of physical or mathematical theories. So that is the goal. In a way, for mathematical and philosophical reasons, one can never really talk about ontology just on its own. So that's again a separate discussion. Here, my goal is to say something about the foundations of physical structure. and based on that, on types of physical theories that can be realized using that physical structure. And for that purpose, I strongly feel that there has to be a mathematical formalism to describe where this physical structure comes from. Okay, so now in this kind of in this kind of system of using intuitionistic logic as a natural choice for a proof system, what happens is that when you have such a formal system, statements about physical observables are simply formal propositions in this formal computational system. So, now, in the same sense, okay, for example, in examples of formal systems that you may have seen in other contexts are usually, they are not the only ones, but those are probably the most familiar examples. If you look at certain systems of logic, there are many types of systems of logic, the standard ones or slightly more interesting ones. And of course, you can realize logic on many things. You can just take some symbolic alphabet, and you can realize some logical operations on them, or you can just say that you have some kind of your basic objects are various kind of things that you may call a set and set theory, and then you may have various operations between them. So there are various ways one can realize logic. So a logic is a formal system, and this formal system you can then use to prove things, or proving things is just the same as writing a computer routine. So within this formal system, you have propositions. A proposition is a statement. In this case, to be in the case of logic, it would be a logical statement. And this logical statement is within such a topos theoretic setup. Such a proposition is a statement about the physical observable. So in this for instance, you may, within this kind of topos or category, you may say that there are certain objects which are formally called state objects, and certain objects which are called value objects. And when you have a map or a morphism, as it is sometimes called, or a relation, if you like to think about it, from a state to a value object, that realizes a physical observable. So again, to give you the simple intuition, in classical physics, the state object would be the phase space, the value object would be, let's say, the real numbers or the complex numbers, or the set of domains within which physical observables may take values. And physical observables like momentum, position, or other things are just maps or morphisms from the general state object to the value object. And a proposition about a physical system is some kind of statement where you're saying that a physical observable of some kind, like a momentum, takes certain values. When you say take certain values, you mean that when you restrict to some part of phase space, this particular map takes some value as whatever that may be. So that kind of proposition expressed very formally is a statement about the physical observable. So this is a way in which formally you may express kinematical statements about a physical theory. Now, the way this kind of formalism is not directly going to just start with Newton's laws. It will start with the basic structures and tell you what kind of mappings between these basic structures realize kinematics and dynamics. Now, this topos theoretic work on its own did not ever go to the point of dynamics. It only discussed kinematics in terms of logical propositions. So every logical proposition about the building blocks of that system gives you a realization of some physical observable. And later on, what I'll try to tell you is that our rewriting systems that we use precisely provide the missing dynamics to these kind of approaches, and not only the missing dynamics, but also a little bit more. Okay, so this is what this kind of formal thinking allows you. Within this kind of formal system, you can make a formal, a logical or a formal statement which expresses something about the system. You can do similar to logical operations. You can perform all sorts of operations on these formal statements, and those are equivalent to kinematical operations upon observable. So maybe you say that you're describing a system that has momentum of within some range and position of within some range. So you combine two formal propositions, and that is the statement that you're talking about a phase space with this value of momentum and this value of position and so on. So this way, classical mechanics and also quantum mechanics separately can be described within this formal framework. But if you see this formalism, and you're welcome to look at those papers of Isham and Doring, you'll quickly realize they are not trying to derive Newton's laws. It's nothing at that level. It's at the level where it tells you where the structure comes from. And if all this would not exist, then the real problem would be that Newton's laws would not really manifest in any mathematical universe. For the standard phenomenology and mechanisms of physics to exist, you need some formal mathematical setting. Again, I'm not going to now delve into some philosophical discussion of whether you think mathematical reality is a reality or not. That's like a separate question. But this is the kind of formal basis to support existing physical theories. And at least the point at which these people got is they tried to show what is the topos theoretic setup for classical mechanics and separately for some aspect of quantum processes or quantum theory. Of course, now we want to do more, and that is why in the physics project we want to go a little bit beyond that. So let me introduce a few more definitions of things. Let me say a little bit about formal languages. What is a formal language? A formal language is essentially a collection of well-formed strings over an alphabet. Think about it similar to what you think about a usual language, like any language that you speak. They all have some, while they are very widely different and interesting in their own right, they all come from some kind of abstract compositional building blocks. You have an alphabet with a set of letters. And with these alphabets, you have certain rules. That rules are either grammatical rules or rules of how certain letters can be formed together to form strings. And you may even have some rules for the strings themselves, which are the strings are the words, and the composition of words are the sentences. So you may have at various levels, you may have some ways in which letters can compose to only give certain words. So a very abstract example would be, let's say that you have a language of two letters, A and B, and you can have all kinds of compositions, AB, AAB, AB, ABB, whatever, all kinds of possible things. Those are all words of a language, and they are infinitely many. Or you may have some kind of rules that every time I have A square should be replaced by A. If you do that, then every time you have AAB, it will be equivalent to AB. And then again, but even then you'll have infinitely many words, but now you have some rules to constrain what words can be formed. So a language is basically a theory of compositions with some grammatical or algebraic relations, which tell you what kind of words can be formed or are allowed in that language, what kind of sentences are allowed, what kind of structures are allowed. So it's a purely syntactic structure. It is not having any geometric or topological essence to it. It is purely syntactic. And this is what we are going to go after. In some sense, Wheeler had this in mind, but he didn't have the framework. What we are trying to suggest is that something syntactic, which is so abstract that on its own, it's just symbolic system of relations and nothing more. It has no physical meaning. It has no geometric or topological meaning. And that should be what best describes some of the kind of thinking that Wheeler, Isham, and others had. And it gives you the mathematical framework for building these foundations upon which physical structures can be realized. Now, we don't want any formal language. We want a language which has a little bit more properties. So we'll equip our language with a deductive system that is called a proof system. A proof system will have axioms that hold within the language and inference rules. Now, this shouldn't be a surprise. If you have all the words of a language, and axioms or inference rules basically tell you that what are the starting initial conditions, and the inference rules tell you what implies what. It tells you some rules of implications. And with that, just a few axioms and some bunch of inference rules, you basically have a proof system. Proof system meaning you can now start saying things like, is a given word equivalent to some other word or not? And to say that, you have to build a proof from one to the other within a finite number of steps. And as you see, this is very computational. If your proof takes infinitely many steps, that means you can never complete the proof. The problem is undecidable. In a finite number of steps, if you can prove, then you say, yes, there's a positive answer. Or for some reason, if there's a way to show that these are not equivalent, you'll exhaust all the possibilities and show that two words are not equivalent. So a proof system is at its heart a very abstract computational system. And we want a formal language that has that kind of deductive system. So we will call this a computational language. And now also to generalize a little bit more, a language doesn't just have to be symbols like you're used to, like ABCD or symbols in any other language, heliographs or something. They can also be graphs, hypergraphs, diagrams, operators, etc. So for example, you may say that your alphabet or the letters are just some some heliographs or pictures, or they may be graphs or hypergraphs, and they may be finitely many or infinitely many. And then you have some grammar, and that grammar tells you how certain graphs can compose to together or not. And this means the grammar will be very restrictive in how you can build these compositions of graphs to get, let's say, larger graphs or more composed structures. So you can have a whole formal language just based on graphs, hypergraphs, diagrams, etc. One advantage of this diagrammatic approach is that instead of working with a language that is just built on letters that we write in a linear way, as if we write from left to right or right to left, whatever, a diagram doesn't have a dimension. You can draw it in 2 dimensions, but you can express it in a kind of dimension-free way, or let's say in more dimensions than 2 or 3, depending on how you can visualize the structure. So these diagrams, when you have diagrams and you have rules for how diagrams can compose and build together, you have a very general class of diagrammatic languages upon which you can perform all kinds of operations, including logical operations. And formal computation or formal rewrite systems are special cases of such a formal language. Within a formal language, you can realize some computational systems, and a particular class of computational systems are rewrite systems. So all this rewriting and all that stuff that you see is really something that sits within such a abstract foundation. So these are formal languages. Now you may ask, okay, fine, this is very general. I may be interested in formal languages or graphs or hypergraphs, but you still need a little bit more. So what we will work with, and this, of course, type theory is now the answer. Type theory serves as a framework for building formal languages, because at the end of the day, what is a formal language? It's just it's just a bunch of there is some initial universe of letters or an alphabet, and there are some relations, and then with these relations you can build all kinds of structure. And type theory is a mathematical framework which is actually it originated more in formal computer science. Much of what I'm saying is very close to the heart of formal computer science, and type theory is at the heart of formal computer science, and it serves as the basic building block of formal languages. Now, what is the main thing? As you know, you can think about it this way. Think of type theory as something that contrasts to standard good old set theory. In set theory, a set is a undifferentiated collection of objects. It follows, depending on how you look at set theory, you might look at it as the Zermelo-Frankel choice axioms, the ZFC theory. And you have a set of which is a collection of objects, and it has some elements which are its members, and you can prove certain things or things about you can prove or unprove some properties about the elements of that set. Okay, all well and good. But a type is a little bit more refined structure. It is the analog of a set, but it has some underlying property to it. So a type to which an element belongs is part of its nature. So in a sense, the word type simply comes from the usual use of the word a type of something, meaning that instead of just talking about a set, like for instance, let's say you can take a set in which you can put a number, you can put a chair, you can put a table, chair, and a number. These things are different. These elements are different, but they are all part of a same set. But in a type, you couldn't do that. A type is something for which the elements are part of something. So you can say the type of numbers is a type. The type of physical objects is a type. These two types are distinct. They are defined by the fact that the type of numbers can only have numbers. You cannot put a physical object in that type. And similarly, and the other way around, the type of physical objects is defined by the nature of what that type means. You cannot just throw any element into that. It can only have certain things that respect that type, which define that type. So it has some property of being of a particular kind, if you like to think about it that way. And in computer science, type theory, or sometimes, as you may have heard of this term called typed lambda calculus in which mathematical variables are not just arbitrary variables, but they are of a particular type. And in some sense, this type, you can also think about this as data type, because in computer science, when you're writing formal programs or formal proofs, you may say that this is of this data type. This data type is, let's say, of integers, or that data type is of floating point decimal numbers. That data type is of a particular kind. It includes maybe irrationals or whatever. So that's what a type is. It's in a sense a data type, and it can only have that kind of property, and therefore you cannot just mess about with the elements of a type. But not only that, think about type theory as what we want to think about type theory as is as really building blocks of formal languages, formal programs, and so on. So if you have a particular type and you have another type, there is no way to say that they are related. So by itself, you have to build a relation between the types, and that itself is another type. So when you compose types or relate types, that itself is another type. So if you take a function, you have the domain of a function, you have a codomain of a function, right? And the functions are mapped from the domain to the codomain. A domain is a particular type of thing. A codomain is another type of thing. And the relation between them is itself another type of thing. And each of them are fundamentally meant to be distinct. You cannot just mix them up. And that is really at the essence of type theory, because with that, every object of mathematics can be built up from that. And I'll give you one example. Okay, so in that sense, type theory works as a building block of all of mathematics. And the formal systems in type theory give you the rules of building proof systems from which you can do formal computations. So let me say a little bit about what type theory entails, and then I'll give you one example of a mathematical object that you can build from type theory. In fact, at the way people look at the foundations of mathematics, they are trying to use these kind of ideas of type theory to build all of mathematics, meaning all of mathematical objects. So if you have a particular arithmetic system, in that arithmetic system, you have certain objects. Those objects by themselves are just kind of they have no properties. You may call them numbers, but they have no properties. How does a number get a particular property? How does it interact with another number in a particular way? How do the compositions or the additions or the multiplications make some sense? All those have type theoretic rules. You have to build up everything from scratch. So if you want to think of an operation like 1 + 1 is equals to whatever, 2 or whatever, you cannot just take that for granted. You have to build up all that process and operations from scratch. And of course, those who are interested, you may look at Whitehead Russell for why the axioms of like the axiomatic foundations of mathematics involve such questions of like something you may like we assume as trivial. Well, 1 + 1 is 2, of course, but behind that there is some deep abstraction, and type theory provides a framework for making some formal sense of such abstractions for building all of mathematics. Now, essentially, so type theory is like a system of it's basically just in the way that you write a formal program. In type theory, you have 4 types of rules. With these 4 rules, you construct everything that you can. It's basically a kind of it's like you go to the kitchen, you have the recipe, you have all the objects, and now you have to build up, you have to compose things and come up with something that looks like a nice meal or whatever. So you have 4 rules essentially in type theory: formation, introduction, elimination, and computation. Similar to if you again look similar to the thinking we use in formal programming languages. When you write down a formal program, you first declare certain symbols, you declare some variables. Then to those variables, you give them some properties. To those properties, you put some rules of substitution or composition. So first you declare a type, then you introduce what type of terms a type can have. Then you allow for rules to manipulate these terms, and then finally some computational rules. These computational rules are precisely like the rewriting rules. So in some sense, type theory is even more fundamental than rewriting, and what we will see later on is that using this kind of type theoretic thinking, we'll be able to express the type theoretic rules of any general rewrite systems, including a multi-way system. So with these building blocks, you can literally build the multi-way system, build the rewriting rules, express everything, and then we'll relate that that kind of formal computation to formal proof theory and to physics. So for an instance, when you start writing a computer program, first you declare a particular type. Like this is the turnstile symbol. It just means that gamma over here is just like the universe of a given universe of mathematics. It could be some within some given mathematical space. This symbol means it holds that type A exists. So you declare the existence of a type. You declare that this notation means that you declare that this type A has a term small a is a term in this type. And as I told you before, since a type has a property, like a type may, for instance, you can say, let's take the type of even numbers. Suppose A is the type of even numbers. If that type has no elements, what it means is that there is no proof of existence of even numbers. To prove that even numbers exist in this framework, you have to show that that type, which is the type of even numbers, it has at least one element, and that would be an even number, because an element in that type automatically gains the property of that type. So when you're proving things in type theory, you have to show that a type of a particular kind, which corresponds to the statement that you're proving, has some elements, and that the existence of those elements constitute proofs. And then there are ways to do that more carefully and formally. Now, just as we do in it's sort of iteratively in other areas of mathematics, even for a type is not a dormant static thing. You can make it dependent on another type. So you can have a type A which has some elements X, and you can have a type B which you have to again first declare that, and that type can depend on the elements of another type, and you can form relations between types. And when you do that, and then once you declare your types and your elements of the types and all the relations they may have, you can then state a little bit about how you may manipulate those types and what computational rules you may put there. So, for instance, if you want to in a formal automated theorem proving system, or in a formal kind of thing, you want to say how do I build something simple like a function? In mathematics, we use functions everywhere. We just take it for granted that a function is some mapping from a domain to a codomain, and we just write down the domain, the codomain. We declare something, we say it belongs to R or C or whatever, and we write down this map, and that's it. And that's how we do kind of day-to-day practical life in kind of standard thing. But if you think deeply about it, it is, and you ask, where does this function come from a very abstract level? How do we build such a function? How do I define it? And then type theory tells you how to do it step by step from nothing, so to say, almost. So for example, I'll just kind of guide you through this thing. You'll get a setting. Now, when I have a statement here, this is like a type theoretic statement, and I put this line, this is kind of an inference step. Given this, we have this. That's what it means. So given this, we have this. So that's how you have to read this. The numerator and the denominator are not divisions. They are just inference processes, like in a formal proof. You could just put an implication, double implication, or whatever, if you like, some other symbol. But in formal proof systems, we write everything on a line. Given this, you have this, you have that, you have that. You just go on and on. So here, these are the rules that we are writing down for a function type. Once you have these rules, you can using some computational routine, import those rules in some formal program and automatically generate the objects of the program. So these rules are not just for fun; they are actually practical in the sense that when you actually look at the machine code of a formal program, that machine code, you may just enter, you may use your keyboard and just enter, okay, here, take a function, give it these values. How does the system know what that actually means? Because underneath that system, underneath that formal program or that programming language that you're using, there's a machine code. That machine code is built on certain rules. That rules compose together, and they automatically do these constructions for you. And what is a function fundamentally comes in that sense. So you can look at it from the point of view of lambda calculus or whatever. So for instance, let's say, in order to build a function from scratch with nothing, you have to first declare a type A, which will be like a domain. You have to declare a type B, which will be like a codomain. You have to declare a type like this, which is a map or an implication from A to B. At this point, this is a type, this is a type, this is a type. There's nothing more to it. it's not yet a function. To make it a function, now you have to start giving it some more interesting properties. So the first thing you'd have to do is you'd have to say that, okay, if I want to start building a function, I have to start allowing for the fact that this type, the elements of this type are such that they at least have some, you want a function, meaning that it is a variable, it depends on some variable from the domain to the codomain. So before even talking about domains and codomains, the objects in this thing, you may call it f, but f by itself has no meaning. So you have to first declare that there are some variables involved in the objects of this. So this is similar notation to lambda calculus. In lambda calculus, this lambda x means that x is a variable within this type. So using this type theoretic rule, you declare that this type has elements. In this case, m could be the element, or you could just say f over here, which depends on a variable x. Then you have to say, okay, fine. So now I have declared that the objects of this type, they depend on some variable, but I still have to relate that to the domain and codomain. So how do I do that? So there you say that, okay, for some given object within this function type and some element a of this type, you now have to say that there is within the codomain b, that is within b, it takes values that itself depend on a. So first you have to just allow for the fact that b itself takes values, or the terms within b itself depend on a, and then you have to say that that dependence on a links to the free variable that you have over here. So to put those together, you need these rules. These triple lines denote a computation. This means that this f that is there in this type, it depends on this free variable, and these f's that you had over here are precisely coming from these free variables here. And when you look at a and b, whenever you have a b, which is a small b, which is in the type capital B, and that depends on a, that dependence is via a substitution, meaning that if you want to evaluate small b at a, then that since b is a variable since b depends on a variable x, when you want to evaluate it at a point a, for that x of b, you substitute a. And that kind of thing tells you that a, when you have a of a particular kind, you get b, where b maps to that a, and that links to exactly this function corresponding to this variable. So you really have to break down every operation like that and write down these rules. And that's what a formal system will understand, that that's what a function is. And in here, I kind of went a little fast, but you can carefully go through these rules. In some sense, what one is doing is that one is basically building these constructions from mathematical inference. And this way you can build other things, like you may build an algebra, you may build more interesting kind of mathematical objects and operations. You may even for example, using this, you may even define what is a simple product, an arithmetic product or an arithmetic sum. You may realize that from these very basic building blocks, and an automated system, an automated formal program, that's what it'll understand. What you and me as human beings, what we use when we think of mathematics, we are often using our own semantics. We have something, we write down some symbols, and then we assign it a meaning. But for a formal system, it has to do it in a syntactic way, a purely syntactic way without any semantics. And that syntactic way means it doesn't understand anything. The syntax has to fully fill in all the gaps of what this thing means and build it from scratch. So that's what type theory is. Now, why is, as I said, I kept saying that this is very closely related to computation. So why is that so? Now, that is, of course, so because of this very well-known correspondence called the Curry-Howard correspondence, which later also became known as the Curry-Howard-Lambeck correspondence. And initially, this correspondence was just a correspondence between formal logic and formal computation, or on this side, proof theory or proofs, and your programs. So it said that proofs and programs have a formal correspondence within the setup of intuitionistic logic. And what they really mean is that from a computer science standpoint, from a computer science point of view, logical propositions are simply types. As I told you, a type is not just a thing on its own. You can compose types and you can build all kinds of types. the same way as you build logical propositions with certain initial symbols, you can use some relations between symbols, like you can use implication, relation, and or whatever, and you build logical propositions from some atomic objects. Same thing you do in type theory. So within the setup of intuitionistic logic, propositions are types. The other way around, not necessarily. So every proposition can be expressed as a type. In that sense, type theory encompasses all of logic and serves as a foundation for that. And in that sense, there is this deep connection between intuitionistic logic and lambda calculus, which is at the heart of all formal computer languages that you use in modern day applications. And of course, now people keep then asking that, well, can we stretch this correspondence further? Can we think of some kind of formal quantum logic which generalizes standard intuitionistic logic, and maybe that is related to quantum calculus and more general type theories, so which are formal objects over here, which may realize some kind of category theoretic logic on the logic side. Now, I use the word categories over here a bit fast, but essentially what it means is that type logic and computation can all be expressed within the mathematical foundations of category theory. And that's why category theory serves as a really useful building block for constructivist mathematics. Now, if you look at lambda calculus more formally, it is expressed in these so-called Cartesian categories. If you look at certain quantum calculi, like the ZX calculus and some of the things that are used in practical quantum computation, those are based on monoidal categories. And if you look at more general calculus, calculi based on type theories, those are based on topos theoretic structures, which encompass, topos is kind of generalize the kind of categories you can have and what kind of compositions you can have. So everything starts getting more and more kind of general. And in a way, as you see, kind of naively, you may think that Cartesian categories with the standard Cartesian product is like the formal system that encompasses classical computation, classical logic. As you start using monoidal categories, you start going into the world of quantum computation, quantum logic, and maybe more general kind of building blocks. And those may be relevant for some kind of physical structures. As you know, monoidal categories are also very useful for so-called categorical quantum mechanics and all kinds of all kinds of tensor networks that people use in some models of holography and dualities in quantum theory. So all these things that we use, that we see in various physical setups, have this deep link between proofs, programs, and physics. And that's again what I want to drive towards. Now, before we actually see how that link works, one of the things I want to now draw attention to this. So far, I've been talking about type theory as if it's just a formal syntactic system. But what's interesting about this formal syntactic system, because compositionality is so fundamental, these formal syntactic systems are not just, they are not just things that you write as syntax. You can express them as syntax, but they have, at an abstract level, a rich kind of topological feel to it. And what does that mean? Just as I told you that type theory, categories, all those things are about abstract syntax and relations between those syntax. Just as you have relations, you can start asking that if I have two relations, what's the relation between that relation? And what's the relation between that relation and that relation? And you can go on. The same thing you can do between formal proofs. You can say that I have two objects. I have two, let's say, elements or terms of type, and I want to prove that they may be equivalent in some sense. And I write a program or I write a proof, and that's a proof that this initial term equals this final term. Then you may say, okay, this is a proof, but is there some other proof which is may or may not be equivalent to this first proof? And you may have a different proof of that theorem, which in some cases may be equivalent to that first proof, but there are many instances in mathematics where two proofs of the same theorem may not be equivalent, and that actually exists. And when that happens, you start realizing that if that happens, you may be very well justified in asking, what is the relation between those two proofs? Meaning, what takes you from one proof to another? And then you may ask, what's the proof between those proofs? Because after all, those are both proofs of the same thing, but they are inequivalent. So there is a way to relate one to another, or there's a relation between those relations. And that's a proof between proofs. And then you can go on infinitely many. you may have another proof between proofs, which is not equivalent to the first proof between proofs. And you may then ask, what's the relation between those? In some cases, they may, in fact, be no relation. They may just be identical objects. In some cases, they may not be. But this begs the question, what does one mean by identity? When are two things identical? And this is not only deeply important for philosophy, but also for mathematics. What does equality mean? What does identity mean? And in a formal system like this, we should allow for the fact that they can be towers of equality or towers of identity. And in type theory, that very naturally gets captured by a slight generalization of type theory, which is called homotopy type theory. Now, I'll say a little bit of what homotopy is. You'll see that. But what homotopy type theory is this idea that you can think of a type as a space. I'm not saying it's a topological space, but you could think about it like a space that has some topological like properties. The points of this space are just terms of a type. This, I mean, at this point, don't think about it geometrically, meaning that it doesn't have to have geometry or anything. This is just a space which has terms. It could be discrete. It could also be continuous. It doesn't matter. There are some terms. There's a term X and there's a term Y of this type. And a path between this is a proof of equivalence between the term X and the term Y. So this path is a proof or a program, however you like to call it, within the formal system that is described by type, within the formal system that describes type A. So you can have a proof, but you can have another proof which is inequivalent to the first proof. And then you may have a relation between those. And you can keep doing that. Now, in this case, if this space is of this type, it has this type of topology, then you may say that, well, this particular path and this particular path are topologically contractible. So they are equivalent. But what if I take another proof, this one here, and there's a hole in between? This path cannot be contracted to this path. So Q cannot be contracted to say path Z or whatever. Then these two proofs are inequivalent proofs mathematically. And you may say that they are not contractible in some sense. They still prove the same things, but they are proofs. So there's an inequality between them, and they are. What this means to say is that there are many levels of what it means for something to be identical or equivalent, and there are infinitely many levels of what it means for something to be identical or inequivalent. In simple systems, when we say that X equals Y, we often say that, well, I may have a proof P from X to Y. I may have a proof Q between X to Y, but between P and Q are identical. There's nothing between them. There is nothing in between that obstructs. I can just shrink P and Q. I can shrink these two paths, and that's it. When you cannot shrink these two paths, then they are not identical, and you have other things. And in formal mathematical setups, all these kind of things can exist. So people quickly realize that there seems to be this nice kind of relation between type theory, set theory, logic, and homotopy theory. Homotopy theory originally is just an area of topology, which had nothing to do with all of this other stuff. Homotopy theory, like in topology, is just a theory of spaces. It studies certain properties of, you take a certain space, it has certain points, elements. You can do some operations. You just basically do a spatial kind of operations on that thing. But people realize that because type theory, logic, set theory, etc., have all these characteristics where you can take relations, you can say talk about relations between relations, you can talk about proofs between proofs, you can say up to what level are two things equivalent or not. Because you can do all that iteratively or sort of building up in a nested way, it's almost like this idea of topology seems to be inherent within what types can do. So in that sense, they realize that this more general correspondence is such where a set is sort of the analog of a type, and a type, as I said, there's this link between types and propositions and logics. And in homotopy theory, a type can be thought of as a space. An element of a type is like a point in that space, which is like a proof of that proposition in logic. And then all the kinds of compositions that you can do between types, like you may have which correspond in logic to logical and or logical or, they have a kind of analog in homotopy type theory as being a product of types or a co-product of types. And for example, an implication type is like a set of in set theory, it's an analog of functions. In logic, it's the analog of, well, the logical implication. And in homotopy, from a homotopic interpretation, it kind of realizes a function space. You have the original types, which are some space, A and B, as I said, and the function space. The kind of the function space thinking is what gives you a implication or a type like this from which you build. So in a way, type theory, when you think of functions and other things like that, or you think of products, co-products, you're thinking about this from this very topological intuition. But type theory is closely related to that. All of these things are just coming from there. And the important thing, I won't run through all of these lines, but the point I mentioned earlier, that when you think about when two terms of a particular type are equal and you want a proof of equality, the points in a particular space are the terms in the type, and the paths within that space are basic formal proofs. And you can start asking when paths are equal or not equal. It's the same thing as asking when proofs are equal or not equal, and how many paths between paths are there is equal to asking how many proofs between proofs are there. And so in formal programming languages, you can build all these kind of constructions of proofs and higher proofs and programs and higher programs. And that has a natural kind of type theory gives you the natural building blocks of that. And that has a nice topological interpretation. But this topological interpretation is not just because, well, it looks nice and it's lovely to think about it that way. It'll actually turn out that this relation between types and topology will become very, very fundamentally crucial for us in trying to realize spaces from pure syntax. And that's what we are after. So let's see how that comes about. So before I actually tell you how spaces come about and how pregeometry, as we think, comes about from this relation, so far, the way I've set it up with proofs, programs, and categories is essentially just this kind of triple connection between proofs, programs, and physics. When you have a formal proof system, you have axioms, you have rules of inference, and you do theorem proving. In a formal program, you have inputs, you have rules of computation, which are the analogs of rules of inference. You execute computation, and you have an output, which you physically do, or nature does, or whatever. It doesn't matter. We are not talking about the ontology of that. In physics, how is this realized? That this formal system or this formal theoretic, whether you want to think of this as a theory or the underlying kind of foundation of physics, you have some initial states, you have the laws of evolution, you have dynamics, and you have the final state. So the laws of evolution are like the computational rules or the rules of inference, and the actual execution of computation or the theorem proving, when you physically realize it, or not you physically realizing it, but when nature physically realizes, when nature emulates herself, then you have these dynamics. And that dynamics is what, from these building blocks, gives you some final state. So in a sense, these symbolic state transition routines model programs in a formal language. And physics, through the lens of such constructivist mathematics, is simply an instantiation of abstract computation. So the statement then is that physics is language theoretic, in the sense that any theory of the underlying fundamental building blocks of physics, the theory of physics, are just expressible as formal languages. And this is how we could understand and build the foundations. It may be another question that in these foundations, how does nature realize physicality? Because all these formal systems, this formal language, etc., these are pure syntactic. Now, you may still ask that from something pure syntactic, how does something that we call physical come about? I will say a little bit about that, and if I don't, just remind me. But so far, everything is syntactic. A formal language is just syntactic. There's no semantics to it yet. Semantics is the key to getting physicality, but that comes later. So, okay, so we have all these syntactic constructions. Before I talk about physicality, I want to actually come to motivating how these syntactic constructions, they are pre-geometric in the sense that there is no geometry, there is no spatiality, they are pure syntax. How from pure syntax can you actually get spaces, mathematical or physical? How can that ever be? How do you even imagine that? So let me say a little bit about that. This is an important question that mathematicians have kept asking, and there are some insights from meta mathematics and the foundations of mathematics, which I'm borrowing and putting it in our context. And I'll try to also show you how these rewriting systems give you a realization of the kind of syntax which for certain types of computations and for certain types of rewrite systems can actually realize such topological spaces. So let's get to that step by step. So to summarize, to kind of understand any kind of physical setup, physical theory, there are two main things you need to explain: kinematics and dynamics. Kinematics involve assertions regarding physical observables in this abstract framework of formal languages, formal computation, toposes. Propositions within a formal language essentially are in fact the expressions of kinematics about that physical system. And dynamics, on the other hand, corresponds to computational rules generated by a proof calculus. So this is our founding framework. We need this kind of computational language, this formal language built type theoretically, which has a proof calculus. That proof calculus allows for state transitions. Those state transitions are basically computations of proof systems using inference rules. Such a proof calculus realizes the abstract notion of symbolic dynamics, and that corresponds to the dynamics as you saw over here based on these laws of motion. So this way, these formal languages express everything, kinematics and dynamics, and this goes a little bit beyond earlier work where people were they still didn't kind of put computation into the game carefully. Within this topos theoretic setting, once you realize that computation via intuitionistic logic is so inherent to the system, you quickly realize that both kinematics and dynamics is right there. But keep in mind, here when I'm talking about kinematics and dynamics, I am not talking about some very kind of practical physical problem like take a ball, you have Newton's laws, you give it a kick from here, it'll go there. I'm not talking about it at that level. I'm talking about this at the level of very abstract building blocks, basic symbolic building blocks. But the world as we know it, except if unlike the Matrix or some kind of film like that, we are not seeing everything in terms of symbols. So there is still the question to answer that from these very primitive building blocks of formal syntax, how do we realize kinematics and dynamics as we know it? Meaning that that one may describe some kind of formal language like this. It may have some interesting objects. It may have some graphs, hypergraphs, and these have some dynamics. But how exactly from that may we realize the kind of realize, let's say, even if not exactly the classical world, but at least some kind of basic quantum field theory or something like that. So I'll have to tell you a little bit about how to think about that, even though we don't have the full answer. But essentially, what I'm trying to press is that for any kind of physical theory you think about, either in quantum gravity, quantum field theory, at the foundations of physics, or at any level whatsoever, you have to ask, where do those structures come from? What are the underlying building blocks of those structures? What is the underlying kinematics and dynamics behind that? And that happens to be these kind of formal languages. Now, let me first give you a few examples and then tell you what type of formal languages are interesting for us. So first, let me tell you about some proof calculi that you are actually familiar with. You may have seen it in various contexts, but you may have used it in such a practical way that you may not have thought too much about it as a formal proof calculus. The first example is what people in quantum computing use. It is called the ZX calculus. These blobs over here, the red and the green, they basically just correspond to generalizations of the poly Z and the poly X operators. And via these operators, you can build all kinds of quantum gates, quantum circuits, and quantum process diagrams. And the ZX calculus is a proof calculus to essentially do quantum process theory, quantum circuit simplifications. Like this is an example of a simple ZX diagram, some of which realize quantum circuits. And based on this calculus, you can do circuit simplifications and you can do all other kinds of problems. Another example are simple rewrite systems upon which the whole of arithmetic is based. So for example, if you take piano arithmetic, you can have some rewrite systems where you have these rules. So these are rules of addition, and the last two are rules of multiplication. You have some basic, you have a zero, which is some well-defined object, and then A corresponds to any other term in the rewriting system. And based on these implications, which are just rewrite rules essentially as you know them, you can perform all kinds of additions and multiplication. Like here, you're adding two numbers. You say 2 plus 2 is 4 or something, and you can realize arithmetic via basic rewrite rules. This is just a quick example that you'll find anywhere. The more familiar rewrite rules that you have seen are for graph rewriting systems. But I mean, here you have seen them explicitly as rewrite rules because they are visuals, but essentially rewrite rules are of this nature, in which these rules perform some operations, and these operations tell you that, like, this is a proof that 2 + 2 is 4, or in this case, it's a computation that 2 + 2 gives you 4. It realizes such a computation. So rewrite rules are meant in formal computer science. They are essentially objects of theorem, not objects. They are essentially mechanisms of theorem proving. And even when we do graph rewriting, we are just seeing initial state to final state because we are thinking about it in the physics sense that you have an initial state, you have evolution, you have a final state. But from the theorem proving point, this is theorem proving. The whole path of these sequences are is a proof that this initial term equals some final term if there is, or if you, depending on how far you're going. Other examples of rewrite systems are hypergraphs, rewrite systems, cellular automata, which you have seen very well. So there are all these kind of rewrite systems which are at their heart inherently computational, and you have seen them directly in the physical interpretation. In this talk, I'm trying to tell you what kind of formal framework they exist within, and all these models that you use where you choose some rule, evolve something. I'm trying to tell you where they live in the mathematical universe and why that universe is the one that gives rise to these structures, and all these syntactic things, how we may make sense of it for more kind of physical and geometric questions. That part will come. So as I mentioned, that these rules of kinematics and dynamics that you see from these rewriting, these are very primitive. You still have to do a little more work to understand compositionality, not just at the primitive level, but what often happens in very interesting complex systems which are not reducible. And also, like in cellular automata rule 30, everything is not reducible. So what will happen is that when you start composing simple primitives and you start building interesting structure, those structures at a coarse-grained level themselves have rules of compositions that didn't exist at a lower level, and those will have their own kind of rewrite system dynamics and so on. And you can have structures of structures of structures with all levels of rules or laws of nature, so to say, that finally realize more interesting things. So if we want to get to the point of describing quantum theories or quantum field theories, it's not just going to come from only looking at rewrite rules at the most basic level. You have to build up some more things. And that's why mathematicians who look at these topos theoretic things, they start looking at toposes, higher toposes, and they try to carefully try to see what type of topos may be appropriate for maybe coming up with with abstract generalizations of quantum field theory, similar to how Isham and Doring were looking at various generalizations of classical mechanics or quantum mechanics. And they are the difficulty in that kind of investigation is not just of exploration, it's also the fact that one quickly realizes that the mathematics that we use to describe many of these formal theories, like even quantum field theory, to discuss a meta theory from where the structures of quantum field theory come up, you can't simply use the existing mathematics of quantum field theory. One needs to generalize the mathematics we know and we use. And therefore, within these topos theoretic frameworks, mathematicians have looked for, say, generalizations of groups, generalizations of symmetries, generalizations of algebras. And from these more general kind of setups, they try to come up with various models of generalized quantum field theories. But for today's talk, I will talk less about the field theory side. I want to talk more about just topology and space and where space comes from. So in this sense, there is this question, where does physics take place? And the answer is that for physics, you have to describe kinematics and dynamics. And the place where you can describe kinematics is a particular type of topos called local topos, where you have some rules of locality, which tell you how things glue together. And for dynamics, you need dynamics is like proofs, but proofs are paths. And for a path, you need that a path be connected. If you have paths that are never connected, or you can never connect paths, then you cannot have dynamics because you cannot have proofs. So you need a particular topos that has this infinite connected property. Like in topology, you have locality and connectedness of topological spaces. Similar to that, in a topos, you need some abstract notion of locality and connectedness, which mathematicians describe as a cohesive topos. At this point, we won't go into the specific details or definition of those toposes. But the point is that there are some special type of toposes which they have identified as the universal constructions where physics takes place. In the same sense, like Turing identified a kind of universal computational machine, mathematicians try to identify the universal constructions upon which all of physics can be constructed, and also all of mathematics. So there are certain types of toposes with these properties upon which theories of relevant to physics can in fact be constructed and built. Now, what is interesting about this is that there are certain types of so-called higher toposes, which are again built on particular classes of type theories, which have a nice kind of homotopical feature. I have to tell you in the next slide what I mean by homotopy, but there are certain types of toposes in which one realizes the so-called infinity groupoids. I'll also tell you what infinity groupoids are. Now, those type of toposes on which infinity groupoids are realized are the ones that will turn out to be interesting for understanding where mathematical, meaning topological or geometric spaces come from. So for mathematicians, when they try to ask what is spatiality or where does space come from, they try this approach of what is called synthetic geometry, meaning they try to synthesize geometry or synthesize space from basic building blocks taken from type theory, from formal languages, and so on. And in order to do that, one of the important constructions or one of the important tools turns out to be these infinity groupoids. And I'll tell you what are infinity groupoids, and I'll also tell you how these infinity groupoids actually come out in the physics project, and also how in the physics project this whole type theoretic setting gets related to rewriting systems. So let me first tell you that, then I'll tell you what exactly is the cool thing about these infinity groupoids from which topology can come. So let me just have this interlude slide where we say a little bit about that. So, in standard good old topology, one often says, okay, let's think of a topological space. In a topological space, you have certain maps, and then like these are some points in a topological space. In the conventional way of thinking, you have some map between those points. You can have two different maps between 2 points of a topological space, and you can even have a map between those maps indicated by this double arrow. But then you may say that, well, this particular topological space may even have some exotic properties such that I can have two such maps between these original maps, and I can even have a map between map, which I'm now indicating by a triple arrow. So it's as if this is a one, I won't call it one dimensional, but let me just say this original map is like a one cell. This second map is like a two cell. This is like a three cell, and you can go on infinitely many depending on the type of topological space. The type of such maps you can have, meaning the type of higher cells that a topological space admits, literally tells you everything there is to know about the topology of that space. So initially, when mathematicians were studying these kind of maps within homotopy theory, because homotopy theory is the study of such maps and their deformations, in a way, this map is just a path. If you have these 2 points, this is a path between this. So this is a path between path and a path between path. Now, intuitively, we often think of a path as a one-dimensional kind of object, because we are thinking of this, well, there's a topological space, there's a path, it looks so one-dimensional. Then you have a path between paths, it looks like a two-dimensional thing, so it's like a two cell and so on. So as soon as mathematicians realize that, well, I mean, if I want to classify a topological space and know everything there is to know about it, I just need to study the paths that you can draw upon the space. And on some spaces, you may not be able to draw more than this two cell, meaning that space itself is like a two-dimensional space. That initial space, if it's two-dimensional, you'll never be able to draw a three cell on that space. But if there is a space which is of higher dimensions, so to say, by dimension, I'm using the word dimensions a little loosely, but if it has some more structure, you may be able to draw more. And there may be some spaces, some exotic topologies on which you may be able to draw infinitely many such cells, the equivalent of infinity paths, and they may even exist. So this means that there are some topologies where in some infinite such maps can infinite hierarchy of such maps of infinite cells or infinite dimensions, as you like, can be constructed, and those turned out to be interesting because these are well-defined, nice topological spaces. Then mathematicians also realize that, look, we are using these things to study the space, but actually the whole logic is the other way around. these maps, these paths between paths, these cells, these homotopies, these are fundamental, not the space. These things define the space, they realize the space. Once you know this, you know everything there is to know about the space. The space is just a thing that we intuitively interpret via our semantics. But what's the real thing are these paths. We should think of these as fundamental. Of course, this is a choice. I mean, you can do you can either way you imagine, mathematics is like poetry. You can start with one stanza and go to the other, or the other way around. So so you can do it both ways sometimes. So once they started realizing that maybe we should think about these paths as fundamental, we should start coming up with some kind of formalism for the space of paths. And the space of paths is sometimes called a groupoid. And when you have these paths to n levels, you have an n groupoid. And when you have these paths up to infinite order, meaning infinitely many cells or infinite homotopy, then you call it an infinity groupoid. So this infinity groupoid is nothing but the data or the collection of infinity paths to infinite order. And of course, it's called a groupoid because it generalizes a group in some sense. But at this point, you may just see what a groupoid is. It is indeed a generalization of a group in some sense. And an infinity groupoid is a generalization of the standard groupoid. But essentially, for our purposes here, the intuition is that this collection of paths, or this data of paths, forms a n groupoid, or an n-dimensional groupoid, if you like to use the word dimensions a little loosely for your intuition. So once you have these infinity groupoids are extremely useful, because there is in fact a hypothesis from Alexander Grothendieck, one of the greatest mathematicians of all time, you could say, one of them, if not the only, who lived in the early parts of the century. He came up with this homotopy hypothesis that said that infinity groupoids actually define topological or homotopy spaces. Infinity groupoids are mathematically equivalent. So once you have an infinity groupoid, it has, because of this paths between paths at an infinite level, it inherently defines topological spaces, at least at the homotopy level. And so if you want to study, if you want to ask what may be the fundamental construction of spatiality, one should look at infinity groupoids. So now, of course, when you have an infinity groupoid has much more structure than an ordinary space that you have. It has so for example, in an infinity groupoid, you may have to slice it and section it in particular ways if you only want to probe some subset of it. But an infinity groupoid has all this data, and that realizes topology. Because if you just take a path, let's say of order 2 or order 3 by itself, it may or may not define a topological space. You may just take these paths abstractly. You may take one path, another path, and a path between paths, and that's it. There's no guarantee that that's going to that is sitting in a topological space, or that realizes a topological space. But once you have an infinity groupoid, you actually have mathematical reasons to think that is it sort of gives you it is an equivalent of a topological space, or you can say it's a conjecture, or you can say it gives rise to the emergence of topology, if you like to think about it. Mathematicians, of course, think about this as an equivalent, that a topological space is fundamentally an infinity groupoid and nothing else. And then once you want to probe the groupoid, you can probe it in various ways to realize smaller structures. But without that infinite tower, you don't have a topology. And then if you want to build geometric spaces synthetically, you have to put a little more property into that infinity groupoid. Now, these infinity groupoids, like earlier, I told you about these toposes and about these categories. But when I spoke about categories, now you can actually start connecting everything together. When I spoke about category, I said, well, the objects don't matter. What matters are the relations. The relations are like things between maps between the objects. Now, whatever I told you, let's just quickly switch gears and take the category point of view. If you do that, let's say that you have a category of objects, you have some relations which are maps, and then you have maps between maps. So you see the category theory setup of whatever we spoke about relations is exactly captured by these infinity groupoids. And if these infinity groupoids realize topological spaces, then our higher categories with these higher relations basically give you topological spaces. And for that reason, these infinity groupoids, which are syntactic objects within a formal category or a formal program, give you the realization of spatial structure. So within our computational routines, our rewrite rules, etc., if one can show you how these infinity groupoids are constructed by, let's say, some rewriting rules, then based on the type of structure you can construct, you actually have a computational realization of topology and spatial structure from rewriting systems and computation. So let's give a concrete realization of how that comes. So let me first take a multi-way system. But I don't want an ordinary multi-way system. I will, of course, want a special kind of multi-way system that gives me a sense of infinity groupoids, meaning I want to realize a multi-way system as an infinity groupoid. But an infinity groupoid is just the data of infinity paths. So I want a multi-way system where I can have the notion of paths and paths between paths and so on. Now, an ordinary multi-way system like this, you may say that, well, I mean, indeed, if I just take these objects as in this case, I've taken a string substitution one, but you can take any other. If I take these objects as terms and I take the causal relations as paths, I already have I already have something that is, in this case, just an ordinary groupoid. And now the question is, how do I start building a higher groupoid out of these multi-way systems? So let's do that. But before doing that, because I want to connect it to what I said earlier, let's not just take the multi-way system as is. First, let me tell you how this multi-way system can be constructed purely type theoretically from pure type theoretic syntactic rules. As in, when you actually use a multi-way system in a computational sense, you have these rules and you have these building rewrites, etc. You just look at them and you interpret them in some way that you see these things as graphs, hypergraphs, etc. You put these things together. But underlying this, there's an automated kind of, at the machine code level, at the machine theoretic level, it's all a type theory. So how does that work? So now, this simple multi-way system you have seen all along. So if you have to type theoretically realize a multi-way system, you may look at the full details of this construction in one of those that literature that I sent. I will not go through all the rules, but I'll just give you a sense. So first you have to, what does this multi-way system, how does one construct this multi-way system from scratch if you have to if you have to construct it from scratch? So if you have to construct this multi-way system from scratch, let me yeah, so you have to first come up with the construction rules of the terms. Then you have to come up with the construction rules of the relations between the terms. Then the construction rules of the rewrite rules, of where the rewrite rules come from. Then you have to find a clever way to store the result of the rewrite and not confuse it, not confuse the terms of the multi-way with the terms of so for example, because this multi-way system can grow and grow and grow, you so to say, you have to first have a separate bag of strings. You have to build a type theoretic setup which constructs all possible strings, then all possible strings and relations between strings. So you have to do a whole bunch of things to build this multi-way system from scratch in a purely syntactic automated way that a computer will know what it is. And you don't have to interpret, oh, this is this or this is this. So how do we do that? So first, we have to construct a monoid of all the strings. A monoid of a string is a kind of simple thing. You define a particular type, a type S, which will be the monoid. A monoid has some rules. There is some identity element, and there are some generators. And then there are rules of composition that given any two generators, you can compose it. And then you apply that rule over and over and over again, and you'll get all kinds of words, which are all the possible strings. And then you may have some equivalence relations that if you compose something with the identity, it remains that element and so on. And so essentially, a monoid is something simpler than a group. And just as you have the axioms of a group from which you can construct a group type theoretically, you can construct a monoid like this type theoretically. So that part is easy. Then you have a function type to generate the rules. So in our multi-way system, you have some rewrite rules. And here I'm just showing a collection of rules together in an abstract way. But for each rewrite rules from the initial to the final, you have to define a function type that actually understands what this function is, which is a rewrite rule, which you will later apply to some of these strings and to the multi-way system. Then you have to declare a particular type, which is a multi-way system itself, and you have to declare what are the terms of this multi-way system. So you have to store the data of this multi-way system with its terms and a separate data of what are the relations between the terms, which are the causal relations. So you have to specify each of those. You have to declare the terms. You have to declare what the terms do. Then you have to declare once you apply the rewrite operations, you have to, because, for example, when you're doing a rewriting thing here, so let's say in this case, the rule is A goes to AB. And let's say you have reached somewhere or at some level 3 of this, and you come up with this particular string, which is A, B, A, B, B. Now, if I ask you, okay, so how do you do the rewrite? What will you do? You will scan the string, and as you're scanning the string, you look for all the A's, and wherever there's an A, you will replace it by AB. And once you get that AB, you will accordingly you will come up with a new term. And then, of course, you will have to make equivalences between terms that are similar. So all these steps, how do you express them automatically in a syntactic way that a computer will understand? That's what we are doing type theoretically. And so if you think about it, I mean, when you look at this, you simply just read it and, oh, it's so simple. But to automate it is a little more work. And that's what this formalism is about. And then once you build up all these rules, you have to apply these rules, you have to apply these conditional statements, you have to build a automatic sequence of what it means to take a string, to scan it, to apply the rule to every place where there's a positive hit, to replace the A by the AB, and to come up with a new term, with a new string. And then you have to say where to store that string, what's the relation between this new string and the old string as a causal relation, and how to keep this data together in the multi-way system, which is itself a type. So you have to do all these processes iteratively again and again and again, and you have to build these type theoretic rules. And once you have these rules, the rules such as the rules of inference, the process of computation is simply the application of these rules again and again and again, and it realizes the multi-way systems in an automated fashion. So there's a whole bunch of things you have to do like that, and that's how you realize the multi-way system type theoretically. Now, you may not worry about that, but at the formal level, at the machine code level, that's what the formal language is that realizes this thing. And now here, we are not worrying about you sitting on your computer, but if nature is realizing computations, then there is an underlying formal language, which may be the language of nature or the theory of nature or whatever, which is realizing these things in this way. And this is a way to mathematically describe and understand it. Okay, so now let's take this example more concretely. We have understood how to do this type theoretically. Now let us understand how to realize higher order paths in this multi-way system. So let's take, again, we take exactly that same example and do this as concretely as possible. So in this multi-way system, the original rules just gave you those standard paths and nothing more. But what you need to do is, if you take two parts of this red one and yellow one, which are already there in the original multi-way system, now you want to start constructing a path between these paths. How would you do that? The way to do that is that you have to actually start adding new rules to that multi-way system. How you may say, how do I guess those rules? First, let me just tell you what how to hack those rules, and later you can then see how those rules could be. Let's say you look at these terms that are there on the red line and the yellow line, and based on these strings, you come up with rules that link these strings together. So you have new rewrite rules that you, after the fact of the multi-way system, the original multi-way system, you add new rewrite rules, and the addition of these new rewrite rules produce a new kind of paths, which are these purple paths. Now, as such, these purple paths, they just look like, well, they themselves are just one-dimensional paths. But the composition of these purple paths with the red and the yellow path realizes a two-cell. This is like, this square is like a two-cell. I'll tell you how the square is a two-cell. And similarly, if you add more and more rules, you can build 3 cells and 4 cells and higher cells. So you may be able, like described in the paper in which this work is published, you can just read off the original multi-way system and start adding appropriate rules that realize higher and higher order cells. Now, if it was not you doing it via this algorithm, if you were to start off with an original rewrite multi-way system where the rules were not just A goes to AB, but all these rules were there from the start, then you would precisely get this kind of some kind of higher order paths like this. So an appropriate choice of rules in any given in some appropriate given multiway system, wherever such rules are computationally allowed and so on, you still need that. It may not happen all the time, but they are, because, well, certain multiway systems may terminate, certain things may not allow higher paths and so on. But on multiway systems where such infinite computation is possible, there you have the possibility of infinitely such many rules, and those are the multiway systems which we call in our paper, we call it Rulial multiway systems, and those give you the computational realization of infinity groupoids because they are precisely a higher homotopy type. Now the actual formal correspondence between that multiway system and an infinity groupoid comes again by looking at some of the category theory connections we made. So these cells essentially are, in the category theory language, they are basically higher homotopy data. So in similar to homotopy theory and category theory, if you have, for example, if you have objects ABCD and you have some one-dimensional morphisms or maps, when you have a map between a map, that realizes a higher morphism. A higher morphism in a category is the same thing as a higher cell in a homotopy. And for us in multiway systems, it is simply a higher path. And that higher path is precisely what realizes a higher cell. So the moral of the story is the following. If you can find a multiway system which realizes higher homotopies, that will give you that will category theoretically give you, in some limit, an infinity groupoid. And this is just showing one part of that construction, where here, if you have a 2-cell and you have the volume between them, that realizes a 3-cell. Now, I mean, formally, this corresponds to what is called an n-fold category. An n-fold category is a well-defined object. In category theory, you can see the definition in the paper. I don't want to spend time on that, on going through the definition. But once you have an n-fold category, an n-fold category has basically the data of higher order relations. These higher order relations are essentially higher homotopies, and these higher homotopies realize exactly the n cells of any abstract topological space. So in a sense, when you reach the infinite limit in cases where it exists, then you get to the point where you have all the data of an infinity groupoid, and that data realizes a homotopy space via Grothendieck's homotopy hypothesis. So in that sense, it is in that sense that Rulial multiway systems which admit such higher order rules that realize infinity groupoids give you the computational analogs of topological spaces in the same way as infinity groupoids realize topological spaces in higher categories. So that is the way in which spatial structure comes about from computational realization. Now, of course, in homotopy theory and in higher category theory, mathematicians had already known this link between higher homotopies and spaces. Here, what we are trying to show is that computation and computational rewriting systems precisely give you realizations of those mathematical structures, which then realize things. So what this means is that we are not the way these things go. These multiway systems, whichever realize these kind of infinite data, wherever these infinite structures can be realized, give you this this kind of object with all these so-called infinite type of object, which has all the data from which topology can be dug out, and then you have to probe this mathematical object in clever ways in order to read the data from which one can realize various type of spatial structures and various type of kinematics, dynamics, and so on. So instead of trying to say that space is something where you take lines and then you take cubes and then you take pixels and you put them together, here we are saying you build everything to an infinite tower that realizes the space, and then you can slice that in various ways, and then that will give you all kinds of lower order spaces from that higher order structure. Instead of going bottom up, it's taking a top down kind of perspective. So, but nonetheless, to go to this top-down perspective, you still have to do all this building block. It's just that you build all these things syntactically, you keep building, and nothing happens. And in some case, if you hit the right kind of rules, magically, you find these towers of infinity, and these towers of infinity actually realize all the mathematical structures that mathematicians know are good for doing math or good for doing geometry or good. And we say that those are exactly the kind of things that are good for doing physics, because computationally, this is how they can be realized. So this is the way we are kind of thinking of how where space comes from, or how spatial structure should be realized in this formal language, formal computation, higher category kind of setup. And in a way, I will say, I know I'm kind of short on time, so I will try to end pretty fast. I'll have to cut down a few things. I'll just kind of try to do this little fast. This so far, most of what I've told you is pure syntactic. Now, you may say that, okay, so again, all this is pure syntactic and abstract structure. There is nothing physical about it. So what realizes physics? There is not an answer we have now. And I don't think there's an answer that anyone has, but even mathematicians and physicists ask this question a lot. One of the clues, if not, or one of the indications of way to look for in this is as following. Computation is to physics what algebra is to geometry. And what that means is that there is in language theory, between syntax and semantics, there is this nice duality. And that duality between syntax and semantics is also a duality between type theory and the meaning of objects in type theory. Just as meaning comes from some syntax, and there is some duality between abstract objects, abstract syntax, and some meaning to it, something about that, which is known as functorial semantics in category theory and formal language theory, is also relevant to algebra and geometry, in the sense that pure math is just pure algebra. It has no meaning. It has no semantics. It has no truth value. It's just algebra. What gives meaning to it is some semantics in which you interpret it. And you can think about this a little bit more also for ordinary objects like groups and all. Same way, geometry is a semantic. It's not an it comes from it's from a syntactic construction. A syntactic construction realizes some semantics, and that semantics is geometry for the working mathematician. And in many such ways, it seems like formal computation is a semantic, is a syntax, and from that syntax, the observer somehow realizes some meaning to it, and that's the physical world. There's more to fill that gap, and that's a tricky part. But some way, this duality between syntax and semantics is where the kind of the world between the abstract and the physical may be understood to be linked together in some way, which we don't know. At this point, we're not trying to answer that philosophical question, but we are trying to just say, where do spatial structures in physics, in mathematics and physics come from? How can they be realized? What kind of constructions might realize those things? I also wanted to say, without taking too much time, that this kind of things that I've said so far, are mostly to understand how pre-geometric structures can be realized from this formal abstract building blocks and so on. Now you may also say that, well, okay, that's nice. So this is one pre-geometry in this mathematical setup gives you some bunch of tools to start looking at various ways in which physical spaces may come up. But if I actually want to look at some theories of quantum gravity, like causal set theory, dynamical triangulation, or some such other, how do I go about? Now, you may say that, well, I mean, look, all of these theories, they start with some kind of structures. All of these structures you can essentially realize via some rewriting system, like from causal sets to the spin networks of LQGs or the triangulations of CDT or so on. You can almost realize everything from some rewriting system. In some computational way, you may realize this. On one hand, there is this whole pre-geometry from these infinite towers of infinity, which tells you how geometry, spatiality, and so on can even exist in an appropriate formal language, in an appropriate topos. And within that, you may look for specific substructures, like a particular kind of causal set or a particular type of hypergraph. And those may realize the more down-to-earth models of quantum gravity. And of course, now we are coming up, we'll soon release some work where we are showing what type of rewriting rules may be behind some of these pre-geometric practical quantum gravity building blocks. but more of that will come later. And I wanted to say a little bit more about how generalizations of symmetries and field theories are also realized with these higher structures. But I think I will keep that part for you to just read on some of the reading lists. And I'll end with this last slide, which is just summarizing to say that in order to really understand physics from a constructivist foundations of computation and programs, this direct path cannot be seen on its own. It has to be understood via this indirect path, which essentially tells you first how to link formal proofs with programs, which is the foundations of computer science via the Curry-Howard correspondence. Then you have to understand how these formal proofs link to homotopies and spaces via what is part of the foundations of mathematics via homotopy type theory. Then you have to understand a little bit about the higher mathematics that people have discussed in order to understand how these homotopy spaces generalize some of the constructions of spaces that we use in physics. And via these three maps, via these three links, you then finally get to realize how is it that physics and computation at a fundamental level may even be related. And the reason we are going through this exercise is because if you just look at some of these hypergraph rewrites and you just see all the fancy things they do, it may look like, well, these are nice, but this just looks like some schematic things or some kind of cartoon diagrams which are giving some intuition. But behind that, if it were a representation of fundamental physics, I'm not saying it all is. There are lots of rewrite systems that have nothing to do with fundamental physics. But if fundamental physics can really be expressed in that way, this is the formalism and this is the chain of ideas that one has to put together to realize in what sense precisely can theories of physics be realized via computations and via rewriting foundations. And of course, then in this talk, mostly I've just focused on one thing of how spatial structures and pregeometry is realized. But similarly, you can look at every individual model of quantum gravity or some kind of, let's say, some kind of basic type of field theoretic building blocks from which these things come. And then you may have to do a case-by-case study. Whatever I've shown you so far is just, let's say, the start of this. This is a serious mathematical approach at how we may make sense of why rewriting should be relevant for physical theories. And of course, here we've just shown one thing, and this is published work, except for the quantum gravity part, that how a pregeometric structure can come. But there's a lot more to do in now trying to show that from these pregeometric infinite towers, one may be able to, extract simple spaces that are relevant for, let's say, constructing some simple models, and how many of these approaches, many of these kind of hypotheses or proposals or models that we have in quantum gravity today, I would not be surprised if all of them actually have certain dualities and relations, and behind them, they can all simply be expressed by more fundamental rewriting systems. And in a way, that should not be surprising. If we really think that Wheeler's idea of pregeometry is a serious one, and it is really the building blocks of quantum gravitational structures, then it should not be surprising that these very diverse-looking theories of quantum gravity that we are kind of all puzzling over these days, they should come from some underlying common framework, some abstract mathematical framework, which looks like a inherently computational system based on a formal language. So the formal language part is extremely important for this type of thinking. And these type theoretic constructions and computation are what goes behind it. So, okay, so that was the core of my talk. I think we are so short on time. I'm still happy to take questions, but feel free to leave if you want to. Don't feel like you have to stay anymore. And until there are questions, I'll take them. But otherwise, thanks for listening and being patient. Maybe I should just check the chat to see if there's any things. Okay. Well, just speak up. Happy to take any questions. If not, we are happy to also continue your discussion on Discord.
So, one question related to the last item. So, define constructivist physics as the equivalent which completes the diagram.
Your audio is a little bit, it's fluctuating. Can you improve it a bit?
Is it better? Is it better?
Yeah, let's try.
Okay, so you define constructivist physics from the last diagram to make it commutative, because you already know the three equivalences and you define it as a composition, or you also define constructivist physics somewhere separately.
No, I don't. I'm hoping to realize it via the other three. So I am saying that whatever constructivist physics is, it should be defined via the other three, because those are better known, better defined, well-defined things that people have spent decades developing in great detail. That defines constructivist physics. There are approaches like maybe Deutsch or others where they just define constructivist directly. I'm not going in that direction, because there the mathematical formalism is missing. If you directly define constructivist just by taking diagrams and schemas and just doing rewrites like this, it will look a little artificial. It'll look like, okay, these are just diagrams and schemas. So what's behind this? That's why I prefer the other route, because there's a foundation for that. Okay.
Can I have one more question?
Yes, of course.
So can you define equivalence on a set of two sets of rewriting rules, for instance, via equivalence of the group infinity groupoids they are defining, or something like this? Or how would you decide that two sets of rewriting rules are equivalent? Or is there such a notion? Are you thinking of that?
Well, there is this kind of question that people ask: when are two types equivalent? Even before the rules, you can say, when are two types equivalent? And depending on the type of type theory one is using, there are some notions of what equivalence means between types. And there is this so-called univalence axiom of Vovotsky, which kind of tries to answer that when you have a type theory with infinity types allowed, then at what level do you make an equivalence between infinity morphisms? But on the other hand, in good old standard type theory, where you're not worrying about infinity morphisms, you have only proofs up to some order, then you have to define proofs of equivalence between these types, and there are ways then in which you say when two types are equivalent. So in a sense, you're thinking of a higher order thinking in which you're thinking of those types themselves as terms within a higher type. And then you're asking what kind of proof of equivalence is there. Then given that these types have, let's say, proofs or morphisms up to some order, for each order of morphism, you have to ask if the equivalence of that is there, and what's the proof of equality between them. So yes, there are ways to do that. And for each such construction, you have to explicitly write down such proofs. Now, you may also, given that a multiway system is a homotopy type, in the multiway system, we are thinking of a multiway. Of course, in the type theoretic way, the way I showed a multiway system is not just the terms and the causal relations. I'm thinking of everything: the rules, the monoid, the relations, everything as a multiway system in a type theoretic setting. And then you can ask, when is one type equal to another? And then you have to go through this whole type theoretic procedure of looking at equivalences at every object at every level. And then you can say, yeah, these two things are equivalent.
And then you can go one level up, and if you have arrows on rewriting rules, you can study paths on rewriting rules and homotopies.
Yes,
the rule yard, one level.
Indeed. So since you're asking this, if you ask me like this, what type of mathematical object? So the term rule-yard, it has never been really well defined. Stephen just explained it intuitively in computational ways. But in our paper, we didn't use the word rule-yard simply because intuitively people think of it in many different ways. But if you ask me mathematically, what is the thing that comes closest to what looks like the rule-yard? I would say that just as certain multiway systems realize infinity groupoids, if you take the category of all infinity groupoids, which actually gives you an infinity one category, that is the category of all such multiway systems that kind of defines a rule-yard. You can also then say, so what about the rule-yard or the next level, which is an infinity two category, which is the category of all those of that previous infinity category, and so on. So that would be like, okay, you have the Roolyard, then you have the Roolyard of Roolyard, and so on. It would become like that. So I would say that this infinity one category, which is a category of all possible infinity multiway systems or all multiway systems, is what is the closest mathematical construction of what we may intuitively think of as a Roolyard. And then you can ask for other things that are hyper computational in some way. But again, these things have to be better defined, but this is the closest that I would say in terms of the category theoretic perspective. Okay, then thanks everyone. I'll stop the recording. We'll get going, and today there will be okay. So let me close everything, and we can get back to project 2.